Every time we type into a search bar and suggestions pop up before we finish the sentence, that's happening in under 100 milliseconds, faster than one can blink. We've all used autocomplete probably 1,000 times before and never asked once how it is actually built. Today, let's figure it out and design one using Maaraa AI. So before I open the tool, I actually want to understand the number we are chasing here, which is 100 milliseconds. That's not a vague make it fast goal. It's a hard budget, and the interesting part of the problem is figuring out where the budget actually gets spent. Think about everything that has to happen between you typing a letter and suggestion appearing. Your keystroke has to travel to the network, the server. The server has to figure out what you might be typing, rank the possibilities by how popular they are, and send the results back. All of that has to happen round trip, has to fit inside this 100 millisecond. If the network alone takes 40 milliseconds there and back, that leaves maybe 60 milliseconds for the actual computation. This is what's called a latency budget. Instead of just saying be fast, we allocate a fixed number of seconds to each piece of the pipeline, and every design decision gets tested against, does this fit in my slice of the budget? The second piece is how you even find matching suggestions that fast. If the keystroke triggered a full database search through millions of past queries, will blow through the budget instantly. The classic data structure for this is called a trie, sometimes called a prefix tree. Instead of storing words as a flat string in a table, you store them letter by letter in a tree, where every path from the root spells out a prefix. So if you type S, Y, S, the system doesn't search as anything, it just walks 3 steps down a tree it already has in memory and instantly knows every word that starts with SYS, may it be system, sysadmin, or syslog. So that's what makes a sub 100 millisecond even possible at this kind of volume. The third piece is trickier, which is ranking. It's not enough to find matches. You have to find the popular matches first. Nobody wants a rare, obscure query showing up above the everyone's actually searching for. And that popularity data has to update in near real time because trending topics change by hour, sometimes by the minute. So, three things to watch for: how the 100 millisecond budget across the pipeline, whether it uses something like a try for prefix matching, and it should also be fast, and how it keeps popularity ranking fresh without recalculating everything from scratch on the keyboard. So my guess before I generate anything, I think there's going to be some kind of in-memory cache or in-memory data structure sitting very close to the API layer, and because it has to do a full database search every keystroke, and there's no way it hits 100 milliseconds consistently. I'm less sure how it will handle the popularity ranking or the trending updates in near real time. Let's see what Maaraa AI generates for us. Now I will write the prompt. Now let's generate the blueprint. Let's see what it assumed. I'm hoping to see something about query length or the size of the dataset it's indexing, since that affects how big this prefix structure needs to be. 1 million queries, P99 latency of less than 100 ms, 99% time. So here it does not explicitly mentions it, but let's just go over it anyways. Maybe it's in the requirements. Yeah, so these are the requirements. The system must provide autocomplete suggestions based on the user input. That's actually what we want. The system must rank autocomplete suggestions by popularity. Exactly. The system must update the popularity and trending status in near real time. The system must capture and process queries to determine term popularity. So these are actually the things we require. And yeah, let's just go forward with the requirements. So these are the non-functional constraints, and these are pretty much the same most of the time. For example, data durability and P99 latency, uptime, daily active users, single pair points of failure, and system must ensure security and privacy of user search queries. That is really important. Scale to store and process query for popularity ranking. That was exactly what I was talking about. So these are the constraints that we got. Now let's generate the blueprint. So here is the output by Maaraa AI. This is the sequence. Let's go through steps 1 to 6. Here's the read path. This is the one that has to hit under 100 milliseconds. Client sends a GET request with the prefix that hits the API gateway, which forwards it to an autocomplete service. And look, the autocomplete service doesn't touch a database at all. It goes straight to something called the try cage, running on memcached right here. That's exactly the try concept. I can see it's not just an abstract data structure, it's actually living inside a memory cage, which makes sense because that's what makes microsecond level hookups possible instead of a full database query. And right here is a note. This cage is optimized for 100 to 1 read heavy workload. It only keeps the top n terms per prefix instead of every possible match. And it evicts old entries using LRU, which is recently used. So if a term hasn't been searched in a while, it quietly gets pushed out to make room for once people are actually typing right now. Now let's discuss from steps 7 to 12. So what happens here is that we actually hit enter on search and not just type the letters. Post to slash search, and instead of updating the try immediately, it logs the query event and publishes it to a message queue. Kafka specifically and immediately returns a 202 accepted, which means got it, and we are processing this asynchronously. This is the really important detail. Notice the client gets their actual search results back on step 12, completely separating from whatever happens to the logged query event afterward. Updating the popularity ranking does not block you from seeing your search results. Those are actually two different jobs. Now let's trace the steps 13 to 18. And this is the part that I was kind of unsure about. How do trending terms actually update? So here it is. Stream processor consumes batches of query events from Kafka, not one at a time, and aggregates the frequencies and calculates the trending scores. Then it writes back to meta database. That's partition, meaning the data is spread across multiple machines by key. So this doesn't become bottleneck as the number of search term grows. And at step 17 here, right here. This closes the loop. The stream processor pushes updated try node waits straight back to that same try case from the read path. So the popularity ranking you see is not static. It's refreshed by this background pipeline continuously. We just never see the request path itself. So right here is the API specifications. We have it pretty simple right here. Just a get autocomplete that takes a query string and optional limit and returns a plain array of string suggestions. No over engineering is done here, which is correct because we don't need much. An endpoint that gets hits constantly on every keystroke should be as simple and lightweight as possible. Moving on to the database schema. This tab is interesting because it gives three completely different storage options instead of just picking one. First is the Elasticsearch. using its built-in completion suggester, which is basically purpose-built for this exact purpose. First, fast prefix matching at scale. Second is Redis, uh, storing terms in sorted set ranked by popularity score, which is the closest thing to the try in memory we talked about earlier. And third is the PostgreSQL. It's very plain. It uses try-time indexing for prefix matching. This is kind of a boring but reliable option if we do not want to run three different systems. So this is actually smart. It's not saying that which is objectively better. It's showing the trade-off. Elasticsearch and Redis both hit some 100 milliseconds easily, but Postgres is simpler to operate if we do not need it at our scale. Fine. So here's the takeaway from this one. 100 milliseconds isn't a single number we hit with one clever trick. It's a budget we spend across multiple decisions, and every one of those decisions this design made, the caching, the tree structure, the ranking step, all exist because of that one constraint. If we ever get asked a latency bound question in an interview, that's a mindset. We just don't say that we cache it. Instead, we go through the whole design that Maaraa AI just presented us right now. My next video is going to be on e-commerce flash sale inventory. So make sure for tuning into that.